Thank you very much to the organizers for inviting me here, and to the seminar organizers for inviting me to give a talk. Thank you all for coming. So some of you I know, some of you I haven't yet had a chance to meet. Those of you I know well might be bored with the first 15 minutes. I hope you don't fall asleep completely. So I'll talk about extending the Prym map, and with some luck a bit more than that. And this is joint work with Jano, Sebastian Kasalainen Martin, with Klaus, Hulek, and with Radu Lazar. Okay. And Radu is here. Klaus is currently given more or less the same talk from what I understand at NYU, but hopefully Radu will correct me if I say something completely silly. So this is about the Prym map, but we won't get there for a while, so I want to talk about curves. So mg will be moduli of complex curves. So everything I say today will be over C. Unfortunately, many of the things fail if we're not over C. So everything will be complex. Curves of genus G. Okay. This is a stack, and you all know that it's not compact. So you can compactify it. So mg bar, this is a Deligne-Mumford compactification. And if you were to think of what it is that you add to compactify, well, you add boundary divisors. So the boundary of mg bar consists of a bunch of divisors. So divisors, usually I guess called d node, union all the way up to d g mod 2. And d node is the closure of the locus of curves that look like this if you're a complex geometer, or that look like this if you're an algebraic geometer. So this means you take a curve whose normalization, sorry, Janusz, is the genus G minus 1, and it has one node. And if you have a divisor di, well, this parameterizes are the curves that an algebraic geometer would draw like this. So this is a reducible nodal curve, and the complex picture would be this: I G minus I. Okay. So I presume that you all know that. So this is a moduli stack of stable nodal curves, and this is a well-behaved stack. It's a Deligne-Mumford stack, but I don't want to worry about that. I want to worry about what other constructions we have. So if I have a curve C of genus G, I can have its Jacobian, which maybe I'll denote by the Jacobian of C, or I'm sure I'll start writing J of C at some point. So what is the Jacobian? There are many different ways to define it. I don't know, maybe you want to think of it as peak node of C. Maybe you want to think of it as peak G minus 1 of C. Maybe you want to think of it as the space of sections of the canonical quotient by H1 of CZ dual or something like that. Okay. It's up to you. Or you can think of it as a complex analytic construction by integrating one forms explicitly and so on. So this Jacobian is a principally polarized abelian variety. I'm talking about just one curve. So for any curve, I have a Jacobian. And how you think of it is up to you. But you should really think it's a principally polarized abelian variety. And I'll try to define this in a second. I'll remind you, of course, that the definition is that a principally polarized abelian variety is to say that A is a quotient of C to the G by a lattice. A lattice of full rank. Full rank means if I tensor it with R, I get all of C to the G. So it means it's generated by two G vectors which form an R basis of theta to G. That's what it means. And then the polarization theta is an ample line bundle on A such that the dimension of the space of sections of theta is 1. And really I shouldn't take theta, I should take the pair A and the first Chern class of theta is a principally polarized abelian variety. So a principally polarized abelian variety is a complex torus together with the first Chern class of an ample line bundle and with one torus, with one section. Okay? You can think of it in any other way you like. It's up to you. And then, of course, you can consider the moduli of such objects. So AG will be the moduli of principally polarized abelian varieties up to biholomorphisms, isomorphisms, preserved in polarization. Okay. And if you think of the Jacobian correctly, and this is where what Dick said has to be done carefully, you have the Torelli map, which associates to a curve its Jacobian. I'll denote this map J. So it takes a class of a curve to the class of its Jacobian, which is a principally polarized abelian variety. If you are very careful, you should really be careful whether you do peak node or peak G minus 1. The most natural thing would probably be to take peak G minus 1 on which peak node would be acting, so you don't really get a principally polarized abelian variety. You get a torus on the principally polarized abelian variety in a nice global way. But let's not worry about that. Okay? So you have a map that takes a curve to its Jacobian. This is a moduli space of curve. This is a moduli space of principally polarized abelian varieties, and you have a map, and of course you want to know something about that map. The moment you have some kind of morphism, you would like to describe something. So the theorem of Torelli, which has many, many proofs now and all very insightful, and from which you can learn things, says that J is injective. Here you have to be careful to mumble something about on the level of stacks or something about the problems on the level of sets. It's okay. On the level of stacks, it's 2 to 1 because every principally polarized abelian variety has an evolution plus minus 1. But let's not worry about it too much. So on the level of sets, has a map of sets. This is true. What does it say? This says that if you know that some abelian variety is a Jacobian of some curve, you know which curve it is a Jacobian of. Okay? I hope that at some point maybe I'll get to something less trivial. Okay, so that's a map, and you can also ask, well, if it's injective, whether it's surjective for genus G at least 4. This is not surjective for dimension reasons. The dimension of this guy is bigger. There is a question of what the image is, but we don't want to go there. What we do want to go is we want to try, how about extending, try to extend the map J to a map J bar from mg bar to somewhere. Well, hopefully it will be an extension, so this means it will be some compactification of AG. So I want to extend the Torelli map that sends a curve to its Jacobian to Deligne-Mumford stable curves, right? That means I should add something, maybe not, we don't know a priori, to the moduli space of principally polarized abelian varieties. Okay? So let's try to see how that would work. So let's try to see what we should add here. I haven't told you anything about compactifications of AG yet, and now will be the time. So suppose I want to try to understand what would be the Jacobian of a curve that looks like that. I'll start drawing algebra geometric pictures, I hope you don't mind. So this is a curve, which is a nodal curve. It sits on the boundary divisor di. It has two components. So what's the Jacobian of that? And if you think about it, and you can see that it's simply the Jacobian of the genus I guy times the Jacobian of the genus G minus I guy. Okay, I'm being slightly sloppy with how I identify Jacobians, whether they're in degree 0, G minus 1, you may need to worry, but let's not worry. Okay, so this object here is a product of one abelian variety and another abelian variety. And the product of two abelian varieties is a perfectly nice abelian variety. So it turns out that this Jacobian is just a nice principally polarized, as you can check, abelian variety, which is a product. As a principally polarized abelian variety, so the polarization is a product. Okay, so this tells you that if you want to try to extend the Torelli map to a generic point of the divisor di, you can just do it. It just works. And you don't need to compactify AG for that. Okay. You may also notice something that remark that this extension, maybe I should put a bar here because really I'm trying to extend, so it will not be injective on di unless I is 1 and G is 2, in fact. Because what happened? I took the Jacobian of the two components, but I have completely forgotten the point where they got attached. And if I'm thinking of a stable nodal curve, it certainly comes with the data of this point on both of the irreducible components. And I have forgotten this point, so this means it's not a good idea. The only reason it's maybe still okay for I equal 1 and G equal to 2 is because on an elliptic curve I have to worry whether I should really fix a point, and 1, 0 is not such a good space. Let's not worry about it too much. But basically we already see that the extension of the Torelli map is not going to be injective. Well, now let's try to see what the extension would be like on a boundary of the irreducible type. So suppose I take a generic point in the boundary divisor D0, and suppose I try now to define the Jacobian of such a curve. Okay. So how would you do that? Well, if you are a classical expert on Riemann surfaces, and I'm not sure that if you are Riemann you would do that, but if you are Schottky you would certainly be aware of that. If you are Wirtgen you will be quite aware. You can try to do some computation here, and what you would do is you would try to draw the complex analytic picture. So you would draw the picture like this. You would say, well, here's my Riemann surface, and what I'm doing is I choose a cycle here that I'm going to pinch, right? And then you are going to try to look, if you're a classical complex analyst, at the definition of Jacobian, not this way, but very explicit by integrating over cycles. And then you will try to say, well, there is a loop in H1 going this way, there is a loop in H1 going this way. Let's try to see what the integrals of holomorphic one forms look like when I degenerate. And you will see that this definitely is not going to look like a principally polarized abelian variety, in the sense that if you try to just compute the periods, they will go off to infinity. Okay. This should hardly surprise you, because there is an easy example of genus 1. You see, M1 is the same as A1. Moduli of elliptic curves is the same no matter how you look at it. I'm not being worried about stacks here necessarily. And it's not compact. And D0 on M1 bar is 1 point, of course. It's this point, right? And with 0. I start feeling slightly bad because I'm really missing points. This is not very stable, so maybe I should put M11 here and an extra point here. But this is not, and if I look at A1, well, this is a famous picture of the upper half plane quotient by a lattice. Lattice in a different sense now. And this is missing the point at infinity. Right, so this is not compact. I will need to add that 1 point, and that exactly corresponds to the period matrix acquiring an infinity in this picture. Or if I conjugate by tau goes to -1 over tau, you see that this point is actually equivalent to this point. So I don't know whether tau went off to infinity or to 0. And this is what will happen in general. So this is the case, and to try to extend the Torelli map to this locus, to the locus of irreducible nodal curves, you would need to try to compactify AG. So I'd now like to try to start to compactify AG. So I'll do this more or less explicitly, and then I'll try to tell you a little bit about toroidal compactification. So now is probably the time to make the first disclaimer. So the talk will be about toroidal compactification, so the moduli space of abelian varieties at some point, and I will not be able to honestly define them for you. I have tried doing this, and in a nice 5-hour course you can get some idea across. In a 1-hour lecture I have never succeeded. So I'll try to give you some idea of what a toroidal compactification is, but I'm sorry I will never construct one for you. I'll tell you what data goes into defining it, and I will state the results, but not really the definition. So how can one think of degenerations of abelian varieties? So degenerations of, I'm sure I'll keep saying abelian varieties, I always mean, for me, principally polarized abelian varieties. So I can think of my abelian variety A as this quotient Cg by a lattice. I can, of course, change coordinates on C to the G without changing the complex structure on the abelian variety or the algebraic structure. And this is the same as C to the G quotient by Z to the G plus Z to the G times tau. So what did I do? I just chose the first G vectors generated on this lattice to be the basis vectors in the G directions, nothing else, for some tau now, which encodes the remaining G vectors. So tau is a G by G complex matrix. And Riemann's bilinear relations tell you the following. They tell you under what conditions is this abelian variety, is this complex torus, sorry, an abelian variety. They say A is a projective variety. Well, I'm tempted to write if and only if, but if and only if tau can be chosen so that it is symmetric and the imaginary part of tau is positive definite. Okay. If you think about the genus 1 case, every 1 by 1 matrix is symmetric. The imaginary part should be positive. That's your upper half plane. In general, the space of such matrices is called the Siegel upper half space. So if I try to compactify the moduli space of abelian varieties, I could try to compactify this space. So in fact, if you look at this more closely, you will see that the moduli space of abelian varieties is the quotient of the Siegel upper half space by the symplectic group with integral coefficients. Symplectic is related to the fact that we talk about principal polarization, so I have to preserve the symplectic pairing rather than something else. So if I want to compactify AG bar, I could try to compactify the Siegel upper half space in some nice way so that this quotient would still make some sense. This quotient is an orbifold, and the whole thing is a stack. Luckily, I don't have to worry about this so much here because I have an explicit construction of this as a quotient of a nice space. So not such a problem. So I'd like to compactify the upper half, the Siegel upper half space in such a way that the action maybe extends. So let's look at the example of genus 1. So for genus 1, the H1 is the upper half plane, H. Right? And then the action on it is the action of SL2Z, PSL2Z. Okay? And then I'd like to compactify H in such a way that the quotient would just pick up one extra point. I know what this one extra point should be. This should be the point at infinity. I know that this is the point I should be adding if I try to compactify A1, right? So A1 bar will be A1 union the point at infinity, where I think of A1 as this standard picture. Right? Then the way I should compactify this should be by adding the entire orbit of infinity under SL2Z. So SL2Z, PSL2Z, orbit of infinity is Q. it's the rational points, right? Because if you think about what happens is, you just write down the formula, and this is clearly equal to A over C, so this is Q. So this means if I try to compactify AG by trying to compactify the Ziegler-Lappa half space, I should be adding all the rational points here. Not the entire real line, that would not be a good idea. I have to add all the rational points. If I add the entire real line, I'll be really in trouble, because this means I would have added infinitely many points. The Hausdorfficity will not be there, it will be a mess. Okay. So let's try to now go back to the general situation. So suppose I have my matrix tau, which is a matrix, and I want to see how it can degenerate. What I am trying still to compactify mentally the Ziegler-Lappa half space, but you'll see we don't get a compactification. We get some partial compactification of that. We don't add the entire real line, we add some subset. So it could be that some entry here is going to infinity. So I could try to understand what should be the limit as, say, t goes to plus infinity of some period matrices that look like that. So what should it be in some partial compactification? So this corresponds to one entry in the period matrix going off to infinity. And if I think about that, this means if I think of the quotient CG, ZG plus ZG, let's call this tau t, and this is no longer this become longer and longer in one direction, they cease to be compact at some point. So the limit of these things as t goes to plus infinity, you will see that this is really a C star bundle over, well, let's call this entry here tau g minus 1. It will be a C star bundle over CG quotient by ZG minus 1 plus ZG minus 1 tau g minus 1. You can just see this. So imagine that somehow this was 0, right? So imagine that I would just stretch in one direction of the period matrix, and the period matrix were a product. Then I would have a nice quotient in the remaining directions, and then I'll have an increasingly long cylinder in this direction, which at the end of the day will become a C star. Okay? So this is what your picture would be. So this means this is the kind of object we would like to add. There is a problem. This is not compact, right? So we need to compactify it somehow. So if you look at this situation in more detail, you will see that torus rank 1, these are called torus rank 1, semi-abelic variety, semi-abelian variety, is just a fancy name for a C star bundle over some abelian variety of dimension 1 less. This is the kind of object I get here. This is non-compact. As a torus rank 1 semi-abelic variety, and I'm sorry, but this seems to be the standard notation, is a compactification there. Well, it's really a compactification of that. But what it really is, it's a P1 bundle over A with 0 and infinity sections identified with a shift. So the picture you may want to think of is this. So this is my P1 bundle over A. So this is A is a copy of A which is a zero section, and this is a copy of A which is an infinity section. So in fact, if you think of a P1 bundle, this is really a bi-rigidified P1 bundle, has a zero and infinity sections. And then I'm identifying these two sections with a shift. So each of these sections is a copy of the abelian variety of dimension 1 less, and I have identified them. So the object I'll get, if there is no shift, it will look like a product of a nodal rational curve times A if there is no shift. Otherwise, the resulting object no longer admits a map to the base, right? It's no longer a bundle because I have just shifted. I have destroyed the map to the base. But that's the object I get. This object has a nice map to A, so C star bundle, but this no longer does. And this is not normal, of course. It has a bad locus. Why am I telling you all of that? Is because I wanted to do one explicit answer to the problem of how you extend the Jacobian map. So if I take the extension of the Jacobian map and I just naively compute the limit under such a family degenerating, so I'll see that the Jacobian of such a thing will look as follows. So this curve, its normalization is a curve C, which will be of genus G minus 1, and this point here will have two preimages P and Q. Okay? And then the Jacobian of this thing will be the P1 bundle over the Jacobian of the curve C with a shift identifying 0 and infinity sections being P minus Q, which I can think of as a point in peak node of C. Okay? There are always one. No. Okay? So the Jacobian of such a thing is obtained from the Jacobian of the normalization when I take a P1 bundle and I identify the 0 and infinity with a shift given by the difference of these 2 points that I have just glued. So in particular, if P and Q are the same point, then this means that I'm gluing on a nodal rational curve, and then the Jacobian will be a product of the nodal rational curve and the Jacobian of the base. As it should be, because we saw before the Jacobian of a union of two curves is that. I'm not telling you something. I'm not telling you which P1 bundle to take. And you know that there are many C star bundles on abelian variety. So the question is which one? And I haven't told you, because there is one part of the picture that I have completely concealed. I have a polarization. So I should still have a polarization on this semi-abelic variety, which I haven't talked about. And then you can ask, if I have such an object defined this way, will I have a polarization? And it turns out that if you want the family of polarizations to have a nice limit on this, the shift determines the line bundle. So the shift is really a point of the abelian variety. A principally polarized abelian variety is naturally identified with this dual abelian variety. The dual parameterizes line bundles. So the line bundle that I have to take is given by the shift. Maybe minus, I can never remember. Depends on your notation. And this is the only line bundle you can take with this shift so that the polarization will descend there. So you see, if I have a P1 bundle over an abelian variety, of course I can define some polarization there, not a big deal. But the point is I then glue it, and the polarization should somehow be invariant under this gluing. And this will tell me that the line bundle has to be the line bundle given by this shift. Okay? As you can rather believably, hopefully, check. Okay, so what have we learned? We have learned how to extend the Torelli morphism to nodal curves with one node. for the node being separated, it was boring, trivial. We didn't get to the boundary of AG. Now we got to the boundary of AG. So what you can ask now is, how do we go on? And you would imagine that I would now go to the blackboard and say, well, the Jacobian of a thing that looks like this is equal to blah, right? And that's what you would maybe imagine. And for this picture, it's true, because there are two curves here, C1 and C2, and I'll say the Jacobian of this is just the Jacobian of C1 times the Jacobian of C2. C2 maybe is smooth, C1 is no longer smooth, but we know how to compute the Jacobian of C1. And that's a correct story. No difficulty here. Then you would imagine that I would go and draw a slightly more complicated picture here. And maybe this, right? And in fact, I could reasonably try to convince you that I know how to compute that. So you would think that our job is done, and maybe this should also guide us on how to compactify the moduli of abelian varieties, which I never told you how to compactify. But then you might start to get worried, because suppose I have a picture like that, or a couple more nodes everywhere along the way. So what would I do then? And it turns out that it's not very clear. So in fact, there are many different compactifications of moduli of abelian varieties. So the question I'd like, well, this is not the question I want to address, but this is a preliminary question that I tried to set up here, was the following. Given what is called a toroidal compactification of AG, let's call this toroidal compactification AG bar, and I'll put different letters here to indicate which one. So does there exist an extension of the Jacobian of the Torelli map So of course you have a rational map, but the question is, can you define a morphism that extends the Jacobian map where it is defined? And I should say that it extends the map for smooth curves, but since we had really no trouble defining Jacobians in the cases I did, that should extend that as well. So whatever toroidal compactification we choose, and there are choices, it would include this law, this stratum, right? So these things will always be parametrized by points in any toroidal compactification. There is no choice. I'll try to cheat my way around. It can be very singular. Each boundary stratum will admit a description as a certain toric. The normalization of each boundary stratum is a toric variety vibration over the universal family of abelian varieties to some power of lower dimension. That's the most precise thing I can say. And then if you ask me how the strata fit together, I'll say I give up. I mean, there is no quick answer to that, right? So somehow I'll tell you what data you need, but how to associate to this data compactification takes a long time. Okay, so let me tell you some names.
Does it follow that it's a rational map? So, you were describing holomorphic algebra. I was asking whether your description can one see that it's...
Well, I have a map from some. I have a map from some quasi-projective something to something else quasi-projective. And the quasi-projectivity I don't see obviously from these descriptions at all. You're asking about algebraicity or? Huh? No, you're asking whether it's algebraic.
From the picture that you have been giving a very complex analytic picture.
No. Okay, sorry. So I was given a complex analytic picture to motivate what the first steps of such extension would be. For that, I did this, and I did some complex analysis. I didn't argue that what I did complex analytically is algebraic. I could, but I didn't. On the open set on MG, the map is algebraic. It's a period map. It's a periods of a curve. This is an algebraic map. So this is a rational map. I would have to argue that what I did was actually the correct algebraic extension. which it is, but that's not obvious from how I gave it. Sorry. Okay? I mean, it is the correct algebraic extension, but that's not how you would construct it necessarily that way. I mean, this is, of course, I should say about torsion-free rank 1 sheaves or something like that, then it becomes algebraic, and then I have to check that this is the same picture. But I mean, I'm just using this for motivation, so I didn't. But the map from MG to AG is algebraic. Okay, so here are a couple theorems. So the first theorem is due to, well, I think Mumford and Namikawa, and I hope this is an inclusive list of the people who have done it. And this is from 1970s, which says that there exists an extension of the Jacobian map, and I'll put Voronoi here, mg bar to ag bar, and this is a so-called second Voronoi toroidal compactification. It's a name for some toroidal compactification. It's just a name. I won't be able to tell you very well right now what it is. I will try to give you some idea in a few minutes. But the statement is that this Torelli map extends. If I take the second Voronoi toroidal compactification, there is an extension of this map. And this was in 1970s, and you could do it more complex analytically, if you wish. Another theorem is due to Alexeev and Brunyate. And this is 2012 or 10 or something. I'm sure it's somewhere in my notes. 12. Which says that there exists a map, there exists a morphism to the so-called perfect cone toroidal compactification. So you would think, okay, so the map extends no matter which toroidal compactification I choose, and that's not true, because there does not exist an extension. I have to be a bit careful what I mean does not. There does not exist an extension to the so-called central cone toroidal compactification for G at least 8. I don't remember on the spot whether it's great, strictly great, or greater than equal. So what does this tell you? This tells you that even though I was posing a very vague question, the answer actually depends on how I compactify the moduli space of abelian varieties. So I won't tell you yet how to compactify them, but let me note that for G up to 3, there is somehow no choice. All 3 compactifications, Voronoi, perfect cone, and central cone are the same. On the other hand, for genus 4, A4 Voronoi is bigger. It admits a contraction map, contraction morphism, to A4 perfect cone, which is equal to A4, bless you, central cone. And for A5 Voronoi admits a map to A5 perfect cone. I actually don't remember about the central cone. This again contracts something, contracts its voices. And for G at least 6, AG Voronoi, AG perfect cone, I will focus mostly on this too. There are rational maps both ways, because you can just take identity on AG, that's boring, but there do not seem to exist any morphisms. Why do I say do not seem to exist? I cannot prove that there is not a morphism, maybe there is. But the collection of strata here is not a subset of the collection of strata here. The collection of strata here is not a subset of the collection of strata here. So I cannot define such a map in a cheap way. Okay. So these are the results of Mumford and Namikawa and Alexeev and Brunyate, and there is a long, there are papers and there is quite a bit of work that goes into here. There is a similar question that you can study, which is about the Prym map. So let me tell you what the Prym map is, and then I'll state the result, and then I'll spend the remaining whatever 10-15 minutes saying a little bit about what we actually do. So the Prym map is as follows. Suppose I have a curve C, of genus G. Okay? And suppose I have a cover of it, C twiddle, of genus 2G minus 1. This is etale 2-to-1 cover. Okay? If I have such a map, I can have a map from the Jacobian of C twiddle to the Jacobian of C. Okay? Let's not worry. Pick node, maybe. Okay. This map has a kernel. So the Prym is a Prym of a cover, is defined to be the kernel of this map F. But then I'll need to take the connected component of 0. And this is, of course, a sub-abelian variety of the Jacobian upstairs. It's a kernel of a map from there. The kernel will actually have 2 connected components, and I'm just picking out one. Okay. So let now Rg be the moduli space of such double covers. Okay. Given such a double cover, I can of course consider the curve C that it's a covering of. So I get such a map. This is a cover of degree 2 to the 2G minus 1. Because a cover is given by a 2 torsion point in the Jacobian, which is not 0, otherwise you get a disconnected double cover. Of course, I also have a map from this to M2G minus 1. This is where the curve C sits. This is where the curve C twiddle sits. But then I also get a map to where the Prym sits. So the Prym, it's a sub-abelian variety of a Jacobian, so it's an abelian variety. You can ask what is the polarization. And it turns out by a miracle that the polarization is twice principal, and there is a canonical way to choose a square root. So your Prym will be an element of AG minus 1. And this is a Prym map. And this is what I'd like to look at. So the question is as follows. Does there exist an extension of the Prym map from a compactification of Rg to a compactification of Ag minus 1? Okay? So I should tell you what these things are. Well, these are the toroidal compactifications. We have not discussed them. What is that? Well, this is a cover, and you can hope that maybe you can try to compactify it so that it will remain a cover of mg bar. And indeed it's true. You can argue this. This has been done. And this will remain, this is a cover of mg bar, which now will branch over some boundary divisor. The branching will be 2 to 1. This is extremely well understood, the way it works. So we know what this is. So we know this. And I haven't told you what the toroidal compactifications are. Okay? And the first result in this direction is that the answer is no. And this is the theorem of Friedman and Smith in 1980s. Bob Friedman at Columbia and Roy Smith retired from Georgia. Okay? And the answer is no. It says that there does not exist such an extension. Of course, this is a ridiculous theorem. I haven't told you how to compactify. I can always blow up resolve. But what I mean is that for any reasonable toroidal compactification, there is no such extension. Why is that the case? Well, definition. Friedman-Smith N, I'll write FSN, cover is something that looks like that. You have two I'll draw two pictures. One will be this being covered by, so this means two irreducible components intersecting in endpoints. And the cover is, there are again going to be two components, two irreducible components intersecting in two endpoints. So the picture of the cover is that you have an etale double cover of one component and an etale double cover of the other component, and they will intersect wherever they intersect. The picture I would like to really draw here is this. This is a dual graph picture. So a vertex corresponds to an irreducible component and edge corresponds to a node. And so there are n edges here. And the double cover picture will be this with two n edges. Okay, so that's a picture of the dual graphs of the double covers. And the theorem they prove is the following theorem. Then they prove that Prym does not extend to FS2. They prove more. Okay. Why am I so focused on FS2? Because FS2 is a locus that already appears in genus something 3 maybe. And then this means that no matter which of the compactifications I'll take will not help me. They're all the same in that genus, and the map does not extend in genus. Let's check the genus carefully. So FS2 actually means that the curve C will lie in M4, right? Because I take these two guys to be elliptic curves with 2 points, I cannot take them to be rational, it will not be stable. So if they're both elliptic and there are 1, 2, 3, sorry, 3, right? I have two elliptic curves connected by two edges, so the genus is 3. And then the cover is, and the Prym would lie in A2, right? And for A2, all the toroidal compactifications are the same. So they somehow, the correct statement is that Prym map does not exist as a map from M3 bar to A2 bar. Okay? So that's the correct statement. And this should somehow tell you that no matter what you do, you will never be able to extend the Prym map unless you start by resolving this, which you could do, but it's somehow unnatural because this is such a nice space. Okay? I'm sorry. Okay. So that's an example showing that the Prym map does not extend, unlike the Torelli map. The next theorem is due to Alexeev, this was 1980s, Alexeev, Birkenhake, Hulek, and Vologodsky in an appendix to their paper, which says the following: the indeterminacy locus of the Prym map to the Voronoi compactification, whatever that is equal to the union of all this Friedman-Smith loci, closed up. Okay, and I should start with n equal to 2. N equal 1 does not cause any trouble here. However high it goes, I don't want to compute. Okay, so this is a very nice result. It tells you precisely what the indeterminacy locus is. So it's sort of very good. It tells you where the map extends. And then you can ask, okay, so we know the map will never extend, but will the answer to the question depend on which compactification we choose? So we see that for the Torelli map, it certainly does depend, but for these two cases, and these are somehow the two most popular toroidal compactifications, the answer is the same. And if you were to ask people, people would say, well, if it's the same for Torelli, it shouldn't be the same here, why not? So the theorem we prove is the following. This is Castellana Martin, Klaus Hulek, Radulaza and I. And it says that the Prym map to the perfect cone extends to a generic point of the Friedman-Smith locus n for any n at least 4. Okay, so it means that the indeterminacy locus of the Prym map to the perfect cone compactification is not the same as it's here, because here all these loci appeared. Here they didn't. What we would like to say, but which we didn't get for technical reasons, it gets very complicated. Conjecture, and this is a theorem for G up to 5, 6, I forget. 5, let's be careful. It says that the indeterminacy locus of the Prym map to the perfect cone compactification is the union of Friedman-Smith 2 and Friedman-Smith 3. These two will always be there, because if they were in the indeterminacy locus here, in dimension 2 and 3, all the toroidal compactifications are the same. You cannot get rid of that. And the higher the Friedman-Smith 4 locus, the Pryms would have torus rank 4, and then there could be a difference. And that's exactly what we see. So these are the results. Okay. So the Friedman-Smith n loci, they are not contained in each other. Because if you think about the dual graph here, right? So let me try to phrase what it means to be a Friedman-Smith curve in terms of a dual graph, because I wanted to do this anyway. So it means I can take a dual graph of the base curve, I can cut it in 2 pieces, so that each piece will be connected by itself, and there'll be n edges connecting them. And that is not related to there being 2 pieces connected by, n plus 2 edges, n plus 1 edge. So these are different loci. The codimensions go down, right? Because, I'm imposing more and more edges, but they are different loci. No, so they're different. You can, of course, ask how to resolve this map. You can ask how to resolve this map. We can say something here, but we don't go so far either. The other benefit maybe of our thing is that our approach allows us to reprove, to give a way to prove all the other theorems I have written on the blackboard before, the extension theorems. So the approach, techniques, are about monodromy cones. So we take monodromy computations. And what we can do is we can take an extension problem Well, I mean, what we actually can do is with rank 1 unipotent monodromy. And we get a combinatorial condition for extension. So what I mean is that at the end of the day, once you set up the machinery, the question of whether the map extends becomes a question in combinatorics, which is a hard question, which is why we cannot do it in full generality, but it becomes much clearer what it is that you are doing. And then all the results about the extension of the Torelli map and the extension of the Prym map can be reformulated in this way. So for each of these questions, the result is that the period map such and such, the Torelli map or the Prym map, or more generally some other period maps, extend to a certain stratum if and only if a certain monodromy cone is contained in a cone of the toroidal compactification. Okay, so let me now use the remaining 5, which I hoped would be 15 minutes, to tell you what the data of a toroidal compactification is and what the monodromy cones are and what it is that one needs to check combinatorially, and then I will have run out of time badly. Okay, so here is the data needed to define a toroidal compactification. and I will be somewhat sloppy, sorry. So we'll fix a lattice, which is z to the g. Somehow fixing this for the g fixes for all smaller genera, so that's good enough. And then if I look at sim2 dual, then of course GL acts on it. Okay. And then I would like to think about the cone of positive definite quadratic forms. So this is a positive definite. How does this arise in compactifying? Well, you can think that this is more or less the imaginary part of a period matrix, right? It's a symmetric matrix which is positive definite. That's what it is. And this is non-compact. The duals here are so that the things work out correctly. And you would like to compactify it. So what you do is you take the rational closure of this cone. So this means you add semi-positive definite matrices or forms with rational radical. The words rational radical are basically to say that the kernel has a basis over Q. Okay? The kernel of such a matrix should have a basis consisting of rational vectors. This is somehow if for lambda being z in one dimension, C is of course r greater than 0, right? And if I take C bar Q, that's rather boring. That's just r greater than or equal to 0. That's very boring. But if you try to somehow think about the upper half plane, you would see that somehow rationality is what we should be looking at. But anyway, this is the correct definition. And then at toroidal compactification, of AG is given by a GL invariant decomposition of this rational closure into convex polyhedral cones. With finitely many GL orbits. Okay. So what does this mean? This is a cone. It's something about positive definiteness. So if you think about 2 by 2 matrices, right, the conditions are, it's a symmetric matrix, so the top left corner is positive, and the determinant is positive. The determinant is positive, it's a quadratic condition. So this cone, it's not polyhedral, it's sort of round. And you want to decompose it into polyhedral cones. There'll be infinitely many of them, because you want your decomposition to be acted upon by the infinite group GL, whatever, GZ. But you want it to be finitely many orbits. And when I say decompose, the cones should fit together. A face of a cone is a cone, the intersection of two cones is a face. So I don't want to say this precisely. Definition. Given a quadratic form, positive definite, semi-positive definite, positive definite. Let's be careful. Semi-positive definite form. Take the integral vectors on which it's minimal. then a perfect cone is the cone spanned by the squares of such vectors. Okay, for some quadratic form. So suppose I take a form Q. From this I get vectors. So the Q is in sim2 dual. So I get a bunch of vectors, L1. Well, I'm sure I'll mix up the duals somewhere. Forget the duals. So I'll get some n vectors on which it's minimized. And then I'll take the span of their squares, which again we'll see it in sim2. Okay, there are a couple of duals missing. Okay, so this is called a perfect cone, and the theorem is that such cones for all quadratic forms define an example of such a decomposition. And then if you take the corresponding toroidal compactification, it's called the perfect cone toroidal compactification. So let me go over time another 1 minute and tell you what it is that one checks. So let's talk about the Torelli map. I won't have a chance to say anything about the Prym map. So mg bar has strata, a curve C here has a dual graph, which is a graph, something like that, right? Given a dual graph, I can compute the corresponding monodromy cone. Where will it sit? Well, for each edge, I should consider the corresponding dual element, and it will be spanned by the squares of this. Okay. And then I can check if such cone is contained in a cone of a fan defined in a toroidal compactification. And there are two possibilities. Yes, then the map extends, the Torelli map. And no, it does not extend. Okay? And this is how you can see it. So the question then becomes the following. Given any graph, a dual graph of a curve, that's not much restriction at all, I can compute the corresponding monodromy cone. I haven't carefully explained to you what this means. And then I can check, I should check whether this cone is contained in a perfect cone. And it turns out that this is a combinatorial question that you can decide, and the answer is yes. So for the Torelli map, every curve, every such cone is contained in a perfect cone. In general, it turns out combinatorially that if any cone generated by rank 1 quadratic forms, as a rank 1 quadratic form, these are squares of vectors, is contained in any perfect cone, then this cone is also contained in a Voronoi cone. So what this tells you is that for any period problem where the monodromy is generated by rank 1 quadratic forms, if it extends to a perfect cone compactification, it will also extend to the Voronoi compactification, which a priori is not trivial because it's a different compactification. It's not true that one is the refinement of the other, but it happens to be true. And then you can ask whether a cone is contained in a Voronoi cone and so on and so forth. Okay, that's it. Thank you. I'm sorry I'm over time.